So as we have learned about electricity here, so far we've talked about charge and we've talked about electric fields. And now we're going to go on and we're going to talk about kind of a really abstract concept in electricity, but a really important one, something called electric potential. And our goal that we want to be able to accomplish here is we want to be able to calculate what's called the electric potential difference. And this will make a lot of sense why this is so important, probably to you, towards the end of the lesson here. So let's go ahead and let's talk about what electric potential is. So electric potential is kind of an abstract concept here. There isn't really an intuitive way that you can just understand what it is, but let me kind of use an analogy to explain it here, okay? Instead of thinking about electricity, just for a minute, let's think about gravity. Okay? Picture the Earth and picture 2 points above the Earth, right? Picture, we can see we have point A and point B, and let's say that we want to move an object from point A to point B, okay? So as you can see, going from A to B, B is higher than A, so as you lift it from A to B, it's got to gain potential energy, right? So at point A, it's got some potential energy, and at point B, it would have a different potential energy, right? So in order to change its potential energy there, we have to do work. We have to do work to raise it up to a higher potential energy, right? The same thing if I want to go the other way. If my object is at point B and I want it to go down to point A, we have to do some work to change its potential energy. Now, you can think of a gravitational field in the same way you would think of an electric field, right? So picture the Earth here with a gravitational field surrounding it. Okay, and you can see within the gravitational field, if you're going between points A and point B, we're going maybe along the same line there, but we're moving through the gravitational field, right? Okay. Some gravitational field exists at point A, and some gravitational field exists at point B, whether or not there's an object at those points. And that's kind of the important point there, is that some field exists there whether or not there's an object there, right? Some capacity for there to be a potential energy exists at those points whether or not an object is actually there, right? And this is kind of the idea that we're getting towards here, right? Instead of gravity, let's go back to electricity now. Instead of having the Earth there at the center, let's say we have a charge. And all of this stuff that we just talked about is exactly the same when it comes to electricity, right? If I have a charge at A or a charge at B, I can move them between A and B. It changes their potential energy, right? But those points in space have something about that particular point in space, whether or not there's actually a charge there or not, that would give a charge potential energy at those points, if that makes any sense. And that is what we call electric potential. Okay, just kind of incidentally, for an object in an electric field here, it's not so tough to find the change in its potential energy as it moves between 2 points in the electric field. We can find that change in potential energy by taking the strength of the charge times the strength of the electric field times the distance that it moves through the electric field, right? So if you want to calculate delta PE, negative QED, right? Okay. Okay, so we just mentioned what electric potential is. A textbook definition might tell you that electric potential is the work required to move a charge to that point in the electric field. I find that to be like an unsatisfying definition because work is measured in joules and electric potential is not measured in joules. In fact, electric potential is measured in a unit you're probably familiar with. You've probably heard this unit before. Electric potential is measured in volts, but it's not voltage. Okay, so don't call it voltage. We're going to talk about voltage at the end of the lesson here, but electric potential and voltage, not exactly the same thing. So don't call this voltage. It's electric potential. Okay. Now, electric potential, we use the variable V, capital V, for electric potential. And like we just mentioned, it's measured in volts, and volts is abbreviated capital V. So it's nice and convenient. Both the variable and the unit are both capital V. So that's nice and convenient, right? Oftentimes on diagrams of electric fields, you'll find drawn what are called equipotential lines. Okay, and what that is an equipotential line is a line that connects every place where the electric potential is equal, right? So you recall seeing our diagrams of electric fields with the arrows that either point away from the positive charges or towards the negative charges. Overlaying those diagrams, we can often draw an equipotential lines, right? And what they do, they connect all the points where the potential is the same. And usually, if for just like a single charge, they'll form circles around the charge, concentric circles around the charge, like you can see in the picture here. Sometimes you get electric field diagrams that are a little bit more complex, and the equipotential lines will be a little bit more complex. But, you know, once we've learned a little bit more about this here, understanding those equipotential lines is going to be very important, because if you have a conductor touching two different equipotential lines, it's going to experience, we'll talk about it in a minute here. These equipotential lines are kind of like a contour map. If you're familiar with a contour map at all, maybe you've taken earth science and you've studied a contour map of, say, a hill or a mountain. The lines on a contour map connect all the points along the hill or the mountain that are the same elevation, the same height, the same potential energy, right? And the lines on the electric field map here, the equipotential lines, connect all the places where the electric potential is the same. So they kind of map out, you know, the potential levels, you know, kind of like a contour map maps out elevations. So it's kind of a similar thing there. Calculating the electric potential at a specific point is beyond the scope of what we're going to do in this class. Okay, it's not so important that we be able to calculate exactly what the electric potential is at a particular point. What we're going to need to be able to do is we're going to be able to calculate the difference in electric potential between 2 points. Okay, the difference between 2 points. And the difference in electric potential has a special name we give it. That is what we call voltage. Okay, voltage is the difference in electric potential, or the electric potential difference, right? Voltage, we're going to call it delta V, with a capital V, for like potential, right? So delta V is voltage, and of course it's measured in volts. You'll notice that things that have a voltage that you're familiar with, like let's say a battery, has 2 terminals, right? And that voltage is the difference in potential between those 2 terminals. Or say an outlet, right? It has the 2 prongs. There's a third one, but the third one is just an extra. You don't need it. It doesn't need to be there for it to work. But it's the 2 main prongs, right? There's 2 of them. And the voltage is the difference in potential between the 2, right? So you can't have a voltage with just one thing, with just one point. It wouldn't make any sense to say, what's the voltage at that point? Doesn't make sense, right? Because a voltage is a difference between 2 points. And we can calculate the voltage between 2 points in an electric field. The voltage delta V will be negative times the strength of the electric field times the distance between those 2 points. So delta V equals negative ED. Not too terribly tricky there, huh? All right, so the electric potential there, kind of an abstract concept, but the math that you guys are going to see isn't that particularly difficult. Some simple, fairly simple equations compared to the ones that we've seen in the past there. Hopefully that helps us to be able to calculate the electric potential difference between some objects. So, till next time.